Good morning, students. Welcome to Real Analysis lectures. In this lecture, we'll discuss about metric space and nonlinear space. Okay, so we'll start with definition of what is meant by metric. We all know that metric is actually we have seen already in real is a distance. Okay, so you take m, which is any non-empty set, then a function from m cross m to r is said to be a metric if the following conditions are satisfied. Obviously, the distance between any 2 points should be greater than or equal to 0. So we always try to have intuition of distance between two places and so on. Then these things are easy. You can see that distance between places is 0 if and only if those two places are same, and distance is symmetric, that means from x to y is same as from y to x, and this is called triangle inequality. Distance from any 2 points is always less than or equal to sum of the distance of other two, okay, x comma z and z comma y, right? Fine. And this pair m comma d is called a metric space. Okay, so that means set together with the metric d, this d is called metric, and this set and together with this metric is called a metric space, right? So if you see one or two examples which we have already, the simplest example is that if you can define an any set m, we can always define a metric, namely distance between 2 points you define as 0, obviously if they are equal, and 1 if they are not equal. Okay, then one can easily check that, so you can take it as an exercise, easy exercise to show that this t is actually a metric. Okay, that means it satisfies these four conditions. Obviously first one is true, trivially true, second one is true, third one is also true, and only you have to just check the triangle inequality for distance between x comma y, where it is this. Okay, fine. Now this is a metric and we call this metric as a discrete metric. Okay, so discrete metric means it takes only two values, 0 and 1. Obviously 1 it takes if those 2 points are different, and 0 if they are same. Okay, fine. And the other one which we already know it on real, which is called usual metric. So obviously distance between x comma y you define as absolute value of modulus of x minus y, and again show this as exercise is that show that this is a metric on R. Okay, and this is called usual metric. Okay, so these two metrics we use frequently. One is usual metric, so whenever we say something is usual metric on R, that means it is absolute value mod x minus y, and discrete metric means it takes only these two values, 0 and 1. Okay, there are some other different types of matrices metrics available. Some of the things I have mentioned here, what you do is you just try and make sure that these are all metrics. So almost like 1 2 3 4 different four metrics we have mentioned here. So you just work it out, and if you have any difficulty proving any, if at all any difficulty you have most of the time while showing this triangle inequality, one may have some difficulty, but try, and if you have not got any of this showing difficulty in any of these things are metric, you can ask me, I'll explain next class. Okay, so once we have defined a norm metric, then and a metric space, we can talk about normed space also, normed vector space. So take v, which is a vector, v is a vector space or a field f, then a norm is just like length of a vector. Okay, so norm on a v is nothing but you can denote this, it is a map from v to r which satisfies the following. So this is just like length of that vector, so obviously that should be greater than or equal to 0, and it is equal to 0, x norm x is equal to 0 if and only if x is equal to 0, and scalar times you take alpha x, alpha times x, where alpha is a scalar, and you find its norm. This should be equal to this scalar times multiple, you take this modulus of alpha, and so these are all, and again the fourth condition is triangle inequality. So these definitions are not new to anyone. They should obviously satisfy the minimum whatever we expect, and if it is defined in a vector space, then we say that it is a norm. Okay, and one such norm we already known is that absolute value. As I said, you take mod x, it satisfy all these four conditions which we know already, and R is a norm. Okay, and we'll see some other uh, norms and Rn and called LP spaces. So you take Rn, for example, R2, R3, and so on. So how you can define Rn is n tuples, collection of n tuples, where each xi is a real number. Okay, then one can define three different norms. One is this norm one. Norm one is take the absolute values and then take the sum. Okay, okay, so sum of absolute values of those coordinates is called norm 1. Okay, then norm 2, this we already have it, we know it, this one. This is nothing but just like extension of this. You take sum of squares of those absolute values, then the square root of that one. Okay, this is norm 2. That means for just like if you say you take R2, in R2 you have something like x comma y. So or x1 comma x2, suppose you call it, this is you, if you call it this is x, then what is norm 2 is nothing but you take x1 square, okay, plus x2 square, then you take its square root. Okay, for xn's, if it is Rn, then some of these things and so on, right? Okay, then we can also define called infinite norm. So this is nothing but you take absolute values and take the maximum among all those coordinates. Okay, maximum of absolute values of those coordinates is called, and this Rn you can have three different norms. Okay, just verify whether they satisfies all norm conditions or not. Okay, it is not at all difficult to verify these things. Then the you can, because it is an Rn, you can have, it's like R infinity, that means you have an infinite tuple, or you can call it as a sequence, right? That we define as LP space. Okay, so you take P greater than or equal to 1, then define LP space as the space of all real sequences x, x1, x2, xn, and so on, where they satisfy this condition. That means sum of mod xi power p, this value should be finite. Okay, so that means what is your LP? LP is the sequence, real sequence, such that if you take this value, this series, this should be a finite one. Okay, whenever such things are there, then such sequences are there. So this LP is collection of real sequences satisfying this condition. Okay, and this LP we can define a norm just like how we have defined here for second norm. Okay, norm 2, here we can define norm P. So norm P for any x in LP, this value is finite, so we will define this as the value of this, then take the pth root. Okay, that is the pth norm. And for example, for p is equal to 1 you try, and p is equal to 2, you can check that they are all norms. Here we have given just for p is equal to 1 why this is norm, and this proof is very very obvious, so I just skip that, you can go through it. Okay, but you try to at least prove it that this L2, okay, L2 is a non-linear space. That means whatever we define, that norm is actually L2 is a norm. That is what you tried. If you are not getting, I'll explain. Okay, fine. So what we have seen so far is a metric, and also we have seen a norm. So most of the time, whenever we talk about here, and we can talk about here also, right? So once we have a metric space or non-linear space, then uh, one of the point which comes again and again is called open ball. Okay, just like how we see in R open intervals. uh, Here we will talk about what is meant by open ball, right? So take M comma D, which is a metric space. We have a metric space, then take any element X in that. Okay, and suppose R is any positive real number. Now what is meant by an open ball around X of radius R, or open ball about X of radius R, is nothing but all elements from M such that distance between X comma Y is strictly less than R. So this ball, we call it this as an open ball. This contain all the elements whose distance with X is less than R. Okay, right? Fine. You can also define norm this balls in terms of normal, so that we will show it soon. What you can observe here is that among these open balls, uh, X is always there. This open ball around X always contains this, because distance between X comma X is 0, which is less than R, right? And whenever if you have a set, one set, but you have two different metrics D1 and D2, then we will differentiate by saying the balls are around X of same radius, but with respect to D1 and D2. Okay, whenever we require, we use that. Otherwise, we don't need to mention that D here, right? If you are talking about only one metric, then we don't need to write D. But if we are talking about two metrics on same set, then we have to write D1 and D2 here. Okay. For example, if you take this usual metric, that means D of X comma Y is mod X minus Y, right? Then what is how this? Then you can talk about how your open ball look like in this usual metric D of X comma Y is mod X minus Y. So obviously, one what we can guess, this open ball, because when your metric is same as usual metric on R, then open balls should be same as open intervals. Okay, that you can see here. So take Y belongs to BXR, that is same as the distance between X comma Y is less than R, but distance of X comma Y is mod X minus Y. So that is same as saying that Y belongs to X minus R, the open interval X minus R and X plus R. So therefore, open balls are same as open intervals in R, or usual when you consider usual metric, which makes sense, right? Okay. And if we see this discrete metric here, open balls are behave differently. So you take this discrete metric, that means 0 when they are equal and 1 if they are not equal. Then suppose you take open, we want to see what is this ball around X of radius half. Okay. If you see this one, how it is defined? It is defined as Y such that distance between X comma Y is less than half. Okay. But because what are all Y satisfies this point, D of X comma Y is either 0 or 1. So here this Y such that distance between X comma Y, if at all it is 1, it doesn't satisfy this. So this is same as D of X comma Y should be equal to 0. This set is same as this set, because 1, if this value is 1, it doesn't satisfy, right? So all Y such that D of X comma Y is equal to 0, but when Y is distance between X comma Y is 0, it is same as X is equal to Y. So what we have here is, this is actually a singleton set. Open ball around X of radius half is actually equal to X only. Not only this half, even if you take 1, that means when distance between X comma Y is strictly less than 1, only possibility this satisfies is that X is equal to Y, right? So therefore, ball around X of radius 1 is also singleton, right? And not only that, if you take any R which is strictly less than 1, that I'm also, you can see that it is singleton. Okay, same technique, right? What about if you take anything greater than 1? Greater than 1, for example, here we are taking R is equal to 2, which is greater than 1. then this y such that d of x comma y is less than 2. So 0 also satisfies this condition. Distance between x comma y is equal to 1 also satisfies this condition, right? That means every element actually satisfies this. So therefore your b2 of bx b2 of x is actually the entire matrix space, right? So the moment if you take radius greater than 1, then we are getting all open balls are the whole entire matrix space. The moment we take radius less than 1, we are getting only singleton, right? So therefore what we have concluded is that in a discrete matrix space, there are only two types of open balls are available, either a singleton or the whole matrix space, right? Hope that is clear. So open balls in a discrete matrix space, in a discrete matrix, either singletons are the whole matrix space, okay, whole space M. Okay, so either singleton or the M. M is a matrix space. This is there in what? Where? This is in discrete matrix space. Okay, fine. Okay. So later onwards we'll see why this discrete matrix space is called huge, because here singletons are open. So you have every element, every set is there open, and so on, that we'll see it, right? The same way you can define what is meant by a closed ball. So obviously how you can define distance between x comma y, even if it is equal to r, that element is allowed. Okay, so you can the only difference between open ball and closed ball is the distance can be equal to r also, right? It's an exercise, just check that what you get here is it should be a closed interval, and you try to find what are this one. Make sure when this one, okay, there you may get little difference right here, and this one it must be same as the previous one, and so on. So just try this swing, try to find what are all closed balls for different values in discrete matrix space, right? And you have any difficulty you can always ask me, but you should try and yours. If you take m is equal to R2 Euclidean and D is Euclidean metric, then that is what is meant by Euclidean matrix, x2 minus x1 square plus y2 minus y1 square. Then one can easily check that, or at least you can guess that in R2 what should be your open balls. See in R what is, you have a real line and these are all open intervals, right? But when we have R2, right, what should be your open ball look like? It should be what? It should be something like this, right? Okay, covering all these points. Okay, that you can check here. This is simply, this is an open disk with center x1 comma y1. So this is center x1 comma y1, and what is radius? Radius is r. Okay, so this is easy to check and it is not at all a problem, right? Now, the same way you can define for a vector space how we have defined for norm vector space also. You can, once you have V, this is a norm space. So from a norm vector space, we always have, we can define a metric. How we can define a metric? D maps from V cross V to R, D of x comma y. How you can define in terms of norm? Obviously norm x minus y, this is the way you can define, right? So therefore once we have a norm vector space, we are having a metric, right? So once you have a metric, you can talk about what is meant by open ball in this metric. So therefore this bx ball around x of radius r is nothing but y such that distance between x comma y is less than r, is same as saying that norm x minus y is less than r. Okay, so what are all open balls in norm linear space is y such that norm x minus y is less than r. Here in metric space, d of x comma y is less than r, and so on. So in particular, what is this? B ball around 0 of radius r is nothing but all elements whose norm or whose length is less than r. Okay, fine. And these are all some of the examples. Again, you try. If norm z1 is mod x plus mod y, norm z2 is square root of mod x square plus mod y square, and norm z infinity is maximum of mod x mod y. If you take these three norms which we already defined for Rn, what is thing is you try to draw what is this ball B10 closed ball. Okay, that means how this, for example, ball around 0 of radius 1, you can talk about closed ball or even open ball. Just I will explain quickly one. Suppose in this norm 1, what is meant by norm 1, how norm z1 is defined. If z is equal to x comma y, then norm z1 is nothing but mod x plus mod y. Okay, so what are all elements which will be there here? So therefore this b10 or closed ball is nothing but some y, okay, or you can call it some z, such that this norm z is less than, okay, 1. Norm z is less than 1, and that is what here, right? But what is meant by saying this one is z which is equal to x comma y, such that mod x plus mod y is less than, of course, because it is a closed ball, it is less than or equal to 1. So what are all x comma y in your R2, what are all your x comma y in R2 whose values, some those values are less than or equal to 1? So obviously this 4 points, 1 comma 0, 0 comma 1, minus 1, this will values will come, right? And not only that, you can take this is x plus y is less than, okay, and just I am going little fast, you can check that this will be the this ball, but try different points and see that whether you get this one or not, right? And similarly for norm 2 and infinite norm, you try to find what are all values we get it here, okay, and check this whether this is the correct one or not. X plus y is equal to 1 and minus x plus y and so on, so you take different 4 values and you see you get these values or not, okay. Okay, fine. So similarly, find in norm 2 and infinite norm, what is this ball, closed ball look like? Similarly, this is the m, you take first quadrant is x greater than or equal to 0 and y greater than or equal to 0. That is your m, and in that you define norm 2 and find what is this. So these are all different value balls. You try it, and it is a good exercise to visualize how balls look like in a metric space. Okay. In a norm vector space, it is enough if we know a ball around 0, unit ball around 0. Why? Because the following result. What this following result says that ball around x of radius r, you can always uh, translate from ball around 0 of radius r by x. So you can call it this is translation. And not only that, this ball around 0 of radius r is actually, it is r times ball around 0 of radius 1. This we will call it as, so this b01 we will call it as unit ball. Okay. So therefore any ball around x of radius r is actually, you can get it if we know what is the unit ball in that metric space, okay. And proof is not at all difficult one, it is a very simple calculation one. We want to show that this one, so show that every element here is also here, okay. But how x plus b0 are, this is nothing but x plus y, that means we are adding every element of that ball to x, okay. So using these two notations, one can easily prove it. Suppose take y is in bxr, therefore norm x minus y is less than r. Then take z is equal to y minus x, therefore norm z is less than r. Norm z is less than r means z is in b0r, okay. Right, norm z is less than r means z is in b0r. So therefore y, which is same as x plus z from here, okay, y is nothing but x plus z, so therefore y belongs to x plus g b0r. Conversely, you take this, these are all very simple thing, it is not at all a problem. Take some element here and show that it is there in there, okay. But what you have to understand is that how any ball can be identified in a norm vector space. So if you know what is b01, then you multiply r to that, you will b0 r, then by translation to by adding x you get bxr. Okay. Fine. So this proof I is given all details here, so I am not going through again. This is a very basic calculations. Okay. Fine. Now just like in real, when we say that some set is bounded if it is contained in an open interval, right? So similarly, you take a metric space m comma d, then a subset a is said to be bounded if a is contained in some open ball. Okay, that means there exists some x and there exists some r greater than 0 such that a is contained in this one. Okay, then we say that it is a bounded set. Okay. And you can talk about diameter of a set. This is nothing but, as usual, you find distance between all possible distances from that set, then you find the supremum of that, then you get a that we define as a diameter. Okay. And as a result, you can easily prove that a set A is bounded if and only if that diameter of that set is finite. That means one actual definition of bounded set is what? If it is contained in a, if a set is contained in some open ball, then we say it is bounded. And equivalently, sometimes one can use this equivalent definition as it is bounded if and only if it is diameter of that set is finite. So you can call it A is bounded if and only diameter of A is finite. And the proof, again, it is very basic thing. Suppose assume that A is bounded, then it will be contained in a ball. Okay. Then use triangle inequality several times. Then what you can show is that diameter of A comma B is less than 2r for whatever A comma B may be from E. So therefore supremum is also less than or equal to 2r, which is finite. So therefore diameter is finite. And if at all diameter is finite, say suppose it is equal to r, suppose if it is equal to r, then we can show that E is actually contained in ball around x of radius 2, where x is any point of that set. Okay. So we are able to provide a ball where A is contained in this, right? And here center may be any point of that set, right? So this proofs are not at all difficult once you should know what you have to prove it, right? Okay. So a set is bounded if and only if the diameter of that set is finite, right? Okay. Now, in last class, we have seen in R what is meant by a convergent sequence and what is meant by a Cauchy sequence. Okay. So now we'll see here those two concepts in a metric space M comma D. Okay. What is meant by convergent sequence and what is meant by Cauchy sequence. And in last class, we proved that these two are actually equal. That means if you have a sequence which is Cauchy, then it converges. If it converges, then it is Cauchy. But we'll see whether in a metric space such is true in general. In general, it is not true that not every Cauchy sequence is convergent. We'll see those with example. But definition is follows again with similar lines in how we define in real life. So you take M comma D metric space. Okay. Then a sequence xn in M is said to be convergent. So first, just to understand, I will write convergence, what is meant by convergent in R. In R, what we know about convergence? Like mod xn minus x is less than epsilon. Right? I am not writing all for all n greater than or equal to n naught and so on. But how this is, if you consider this is like a usual metric, right? So therefore, this can be replaced by distance between x comma x should be less than epsilon. So this is the what we require when we want to define in terms of metric space. So distance between xn comma x it should be less than epsilon. This is same as saying that in terms of balls, this should be there. Xn should be there eventually in the open ball, right? Same way you can define what is meant by this is for convergent. And how you can define for Cauchy? In R, what is meant by Cauchy? Xn minus xm should be less than epsilon for all n comma m greater than some stage, right? So therefore, what we can expect here, distance between xn comma xm should be less than epsilon. That's all. So everything what we are defining is already known and we are generalizing from R, right? But when we generalize, it is not necessary that whatever result is true in R is also true in that metric space, right? If something is true in a metric space, obviously it will be true in that R with usual metric also, right? But not the other way. We can see here that is what we are going to prove it. Every convergent sequence is Cauchy but not the converse. So in a metric space, what we know is that if a sequence is convergent, suppose you call it xn is convergent, then we can easily show that xn is Cauchy but the converse is not true. That means, but we have seen in yesterday, it is true in R, right? Okay, but not true in general metric space, right? The showing xn converges implies xn Cauchy is same as how we do it in R. Okay, that means because it is convergent, say xn converges to x, then for epsilon you have a stage xn comma x converges to, is less than epsilon by 2, right? And we want to show that after this stage any two elements are close, so distance of xn comma xm, what we do is we use the triangular inequality with the help of this x and we get this. Okay, so the proof of showing convergent implies Cauchy is not at all difficult one. It goes similar lines with R. Okay, but converse in general is not true. That means you have some Cauchy sequence in a metric space but that need not be convergent. So what example we are considering here is this: you take M is open 0 and closed 1, and this metric is mod x minus 1. That's all. Okay, that absolute value, right? Now in this we define a sequence xn as 1 by n. Okay, so you can think that usually 1 by n tends to 0, right? But 0 is not here, right? That's why it is not convergent. But you can show that 1 by n this are all close enough, so it is Cauchy. Okay, so that is how you can think of, right? So how you can prove that it is Cauchy sequence? So what is distance between xn comma xm, which is mod xn minus xm, 1 upon n minus 1 upon m, n minus m. So we can see that n minus m, this value is obviously less than, strictly less than or equal to n, right? So therefore this value whatever we are having here is less than n upon nm, right? So that is same as 1 by m. So we want to make sure that this is less than epsilon, and such things we already seen. The Archimedean property will give such things, right? So therefore for Archimedean property, for epsilon greater than 0 there exists a capital N greater than 1 by n. Now if you take any m comma n bigger than or equal to that n, then this value we already seen that it is less than 1 by m. So therefore, but 1 by m is less than 1 by capital N, which is less than epsilon by Archimedean property. Therefore this sequence is Cauchy sequence, right? But now we'll show that it is not convergent. So how we'll show this it is not convergent? By a contradiction. Suppose assume that xn converges to x. So if at all xn converges to x, some x in that metric space 0 comma 1, then you know that x is greater than 0 because x belongs to here, so therefore x is greater than 0. So as x is greater than 0, again we can take the help of Archimedean property. So there exists a natural number such that 1 by n is less than x. This is same as saying that x minus 1 by n is greater than 0. So take this as your epsilon. Okay, see, if it is convergent means for any positive epsilon greater than 0, we should have a, that after some stage less than epsilon and so on, right? Okay, but we get some contradiction for this particular epsilon. So take epsilon is equal to x minus 1 by n, right? So for this epsilon, as xn converges to x means there exists some stage n naught mod xn minus x is less than epsilon for all n greater than or equal to n naught, right? But we find some n bigger than n naught, and for that n we show that it is wrong. This is not correct. So what we are taking, you take the maximum of 2n and this together with n naught. Okay, so take n which is maximum of 2n and n naught or anything bigger than that. Then what is the value of xn minus x? Because xn is 1 by n, so it is same as x minus 1 by n, and 1 by n is greater than or equal to, because this n is bigger than or equal to 2n, so minus 1 by n is bigger than or equal to minus 1 by 2n, and which is bigger than capital X minus 1 by n. but we know that x minus 1 by n is epsilon, right? So what we have proved is that mod xn minus x is greater than epsilon for this n which is bigger than 2n comma n naught. That is a contradiction, because whenever the moment n is bigger than n naught, we should have less than epsilon, but here we are getting greater than. Okay, so if you want, you can write here greater than or equal to. So you are getting greater than or equal to epsilon, which is a contradiction, right? That means our contradiction arises because we have assumed that xn converges to x, which is not possible. So in general metric space, not every Cauchy sequence is convergent, but it is true in R. Okay, fine. And other property which we have seen last class is that in R we proved that every bounded sequence has convergent subsequence. Okay, this we have proved it, but that is not true for a general metric space. A bounded sequence, okay, may not have any convergent subsequence. So what is true in R not necessarily be true in any metric space, right? How we do that? You take, whenever we want to say some, this most of the time this discrete metric is very useful. So take R together with discrete metric. Okay, that means distance is either 0 or 1. Then you take your xn is n. Okay, that means 1 2 3 4 and so on. Okay, in R usually it is not a bounded sequence in R with usual metric, but in R with discrete metric it is bounded. Why? Because what is meant by the bounded set definition in metric space, if it is contained in some ball. Okay, so obviously in discrete metric space we have only two types of balls, either singleton or whole metric space, that is R, right? So if I take ball around 0 of radius 2 or anything bigger than, strictly bigger than 1, then what is this one? This is obviously the whole space, right? And hence this xn is contained in this ball. Okay, that shows that this xn is bounded in discrete metric. Okay, whereas in normal usual metric R, it is not bounded sequence, right? But in discrete metric this is possible. So therefore this xn is bounded, but we'll show that this xn does not have any convergent subsequence. We get a we suppose assume that xnk is some sequence which is subsequence which is convergent. So we know that every convergent sequence is Cauchy. Okay, so xnk is a Cauchy sequence, but we get a contradiction to this Cauchy, because if at all it is Cauchy, then for any epsilon, so in particular for epsilon is equal to 1 by 2, there is some state such that distance between these two should be less than epsilon, which is less than half. Okay, but whatever stage it may be, how distance is defined, if those two values are different, then their value is 1. If their values are equal, then their value is 0. So therefore here, if this p is different from q, then x and p is different from x and q, because our xn is n. Is this clear? Okay, so therefore these two are two different values, so that means distance between xnp and xnq is actually 1, which is less than half is impossible, right? So that is a contradiction. Therefore this sequence subsequence cannot be a convergent subsequence. So even though you have a bounded sequence, no convergent subsequence exists for that bounded sequence, right? Okay. And one last result, which is we can easily guess, that whenever xn converges to x in a metric space m comma d, then if you take any y, then distance between xn comma y converges to distance between x comma y. So for any y in m, this is obvious that distance between xn comma y. So remember, distance, once you talk about distance, then it is a real number. So this is a real sequence. Okay, right? And not only that, for any y, if you have two sequences, xn converges to x and yn converges to y, then you can prove that distance between xn comma yn converges to distance between x comma y. Okay, this statement proof is not at all difficult one. How we do is, because we want to show that it is in R, So what is meant by saying that something converges in R? You want to talk about this distance between x and comma y minus distance between x comma y is less than epsilon. So how you can show this here? You show that distance between x and comma y minus d of x comma y is less than epsilon. For that, we use the fact that xn converges to x, oh, in m comma d. So right, therefore what is meant by xn converges to x? Xn converges to x in m comma d implies distance between x and comma x is less than epsilon. So we want to show that this is less than epsilon. So somehow show that xn comma y minus d of x comma y is less than or equal to d of xn comma x. Then we get that this is less than epsilon. So this is the idea, right? And this obviously follows how one can show such things using triangle inequality in this metric, right? That's all. So use the triangle inequality and you get it. Okay. And that proves, and even if you have two sequences converges, then instead of you have having two stages, take the maximum. So after that it will be true for both. So apply then triangle inequality, you get this. Okay, these are the things about metrics and norms, all basic concepts what are all we have seen. So we have seen what is meant by a metric space and as well as norm linear space. Okay, then we have seen some examples, and then we have covered what is meant by open ball. Okay, or you can also call what is meant by closed one. And then we have seen again some several examples about open balls. Then we have seen what is meant by convergence in metric space and what is meant by Cauchiness in that metric space. Okay, and what are the relation among this convergent and Cauchy in a metric space. Okay, so what we have proved is that convergence implies Cauchy, but Cauchy does not implies convergence in a metric space. And the last result which we have shown is in terms of whenever x sequence converges, the other one which we have shown is that whenever a sequence converges in a metric space, then for a distance with a fixed point also converges, right? So we'll, these are the things, and next class we'll see some more properties about metric space. Okay, we'll stop here. Thank you.